Hey everybody, welcome to the Chapter 7 video lecture. Sorry. This one on measurements and problem solving. So in this chapter we are going to be looking at what evidence of a chemical reaction looks like and talking about some typical chemical reactions. There are 5 that we're going to learn the names of and learn how to recognize, and then there are 4 general types that we'll go over. Alright, so evidence of a chemical reaction can sometimes be really obvious. So in classic grade school volcano type science projects, baking soda, which is sodium carbonate, reacts with acetic acid in the form of vinegar to produce carbon dioxide gas and water and sodium acetate. And the newly formed carbon dioxide bubbles of the mixture actually cause the eruption. And reactions that occur in liquids and form a gas, like this type of reaction, are what we call gas evolution reactions. And then, of course, you could put some red food coloring and help see the bubbles. So gas evolution reactions, gotta get my pen to work here. So gas evolution reactions are just one of the 5 types of reaction that we're going to go over. And now my pen works. Okay. Chemical reactions can also be of the combustion type. So, sorry, I wanted to write gas evolution. So, combustion reactions are another type. Now, a combustion reaction, such as the one that takes place in an automobile engine, where hydrocarbons such as octane, C8H16 here, octane, 18, combine with oxygen. So gasoline molecules combine with oxygen from the air and react to form carbon dioxide and water. This is the reactants and the products of a combustion reaction. Now, combustion reactions are a subcategory of what we would call oxidation reactions. Oxidation/reduction reactions, in which electrons are transferred from one substance to another. And again, combustion is going to be another subcategory that we look at. There are chemical reactions that actually happen inside laundry detergent. So let me tell you a little bit about how laundry detergent works better than soap, because it has a substance in it that softens hard water. So hard water is water that contains dissolved calcium and magnesium ions. Not at the same time, they don't have to both be there for it to be hard water, but if these ions are present in your water, we call it hard water. Now, these ions will interfere with the action of soap by reacting with it to form a gray, slimy substance called curd or soap scum. And so you can see here what the presence of hard water does to soap. Now, if you don't have those ions, soap actually forms the bubbles and you get the cleaning action out of it. So if you've ever washed your clothes with ordinary soap, you may have noticed this soap scum on your clothes. Now, what laundry detergents have is they contain substances such as sodium carbonate, which is just kind of like baking soda. Baking soda is where one of those sodiums is replaced with a hydrogen. Sodium carbonate actually will help to remove the calcium and magnesium ions from the water. Once this dissolves into the water, the dissolved carbonate, CO3 2-, in its aqueous form, will react with the calcium and the magnesium to form compounds like calcium carbonate and magnesium carbonate. And then these settle to the bottom of the laundry mixture. They get removed. The laundry detergent then contains substances that will react with the hard ions to immobilize them. And then basically the fact that these solid substances formed in water is what we call a precipitation reaction. So another type of reaction. So redox reactions contain things like combustion. We have gas evolution. We have so forming a gas. We have precipitation. We're forming a solid. We do have acid and base reactions as well, but we'll take a look at those in a second. So how do we tell if a chemical reaction is actually happening? Like if we could see the atoms and molecules that compose matter, we would easily be able to tell if a chemical reaction happened, because we would see atoms combine with other atoms to form compounds, we would see new molecules, we would see the original molecules decompose, so on. If we could see the atoms and the molecules that compose matter, we would know chemical reactions are occurring by seeing these changes. But often these molecular changes cause macroscopic changes that we actually can see, and so we can still tell if a chemical reaction is happening. Now, of those, each of the following that I'm going to talk about here represents evidence of a chemical reaction. So a color change, seeing the color of the solution change. The formation of a solid in a previously clear or unclouded solution. The formation of a gas, this is what we see when we see bubbles forming. The emission of light. So the emission of light looks like this. This is different than the absorption of light. What does the absorption of light look like? Well, look around. You're seeing the absorption of light everywhere. That's why things look different colors, is because light is being absorbed by the material and certain wavelengths are bouncing off and hitting your eye. So if something looks red to you, that's because the blues and the greens are being absorbed and the reds are being bounced back at your eye. So this isn't something that we talk about when we see chemical reactions. We talk about color change. That's differences in the absorption of light, but we don't say, oh, now this reaction absorbs light. On the other hand, reactions can give off light. That's called glowing, right? Things can glow, or they can become bright, right? There could be no light in a dark room and now there's light. Those things are not the same as absorbing light. That's emitting light, and that is definitely chemical reaction. The emission or absorption of heat. So just to be clear, heat can be absorbed or emitted, not light. Heat being absorbed means that the solution gets hotter. Heat being absorbed means that to our hands, the solution feels colder because the molecules themselves are taking up the heat from the solution, making the solution colder. If it releases heat, then the solution feels warmer to our hands because the solution itself gets hotter. So we want to pay attention for those kinds of changes. Now, let's talk about a little more evidence and how we can discern the difference between evidence and non-evidence. So first here on the right, on the left, of the slide, you see two pictures. Now on the left, you see a precipitation reaction, so the formation of a solid when there wasn't a solid before. So this yellow liquid is interacting with this clear liquid, and then right here where they touch, a solid is forming and settling or precipitating to the bottom. Gas evolution, formation of a gas. So something is happening inside this reaction, right? This is a Tums or an Alka-Seltzer or something, some kind of carbonate-containing molecule. This is reacting with the water and it's producing carbon dioxide. So carbon dioxide wasn't stored up inside this little tablet, but it was inside a compound, maybe like, without the parentheses, a compound like this. Yeah, no parentheses. But now it's free like this, CO2. So reactions happening, releasing the bubbles, and we can see that change. Now, what isn't a chemical reaction is water boiling. We see bubbles here, not the same thing, right? We can be fooled, so we need to be extra vigilant. Water boiling does not mean a chemical reaction is happening. Remember, water can change from a liquid to a gas, but it is still water. So really, only chemical analysis will show if the initial substance has changed into something else. Chemical reactions may occur without any obvious signs at all, but chemical analysis will show that it has occurred. Changes occurring at the molecular and atomic levels will actually determine whether a chemical reaction has taken place. When we represent chemical reactions, which we try to do with formulas, we always put the reactants on the left and the products on the right. We often see or specify the state of each reactant or product in parentheses next to the formula. So you can see here in this combustion reaction where we've got methane reacting with oxygen to produce CO2 and water, that the phases are all shown. And we use G for gas, L for liquid, S for solid, and AQ for aqueous. AQ is when we have things dissolved in solution, and we'll really get into that in chapter 13. But it'll come up before then. All right, and then, like I said, the reaction occurring in this example here is a combustion reaction. This is the combustion of methane. And the next thing we do after we've written a chemical formula like this is that we want to make sure that it's balanced, and that means making sure that we conserve our mass. So conservation of mass has to be maintained here. So let's take another look at this equation. This time we kind of see it in a little bit of a different way. We've got molecular models up top and molecular formulas on bottom. So what you're supposed to see here is that the number of atoms on both sides of the equation is not the same. Atoms can't disappear or reappear. They need to all be there at the start of the reaction. So we see here in the reactants we have an O2 that contains 2 oxygen atoms. But then in the products we see that there's some O's in the CO2, but also an O in the water. And if we add all those up, there's 3 atoms of O. So that doesn't match. And again, conservation of mass says that this has to match. And so we need to rectify this. If we look at one of the other atoms, we see that there are some H's in here as well. H's in methane, there's 4 of them. But over here in water, there's only 2. And so it looks like we've gained some oxygens, we've lost some hydrogens, and again, this is not possible. So what we need to do here is figure out how to balance this equation. Now, let me show you what the balanced equation looks like. So to balance this equation, we actually have to insert some coefficients. Those are numbers that go in front of the molecular formula. Now, this will tell us how many of each type of atom or molecule we need as a reactant. So you can see here that we've added a 2 in front of the O2 and a 2 in front of the water. And so we need to see how that has changed everything. So by adding a 2 into the O2s, we've gone from 1 oxygen molecule to 2, so 4 oxygen molecules. And by adding an extra water, we've brought the number of oxygen molecules on both sides to 4. By bringing in a second water, we've also accounted for those missing H's. Initially we had 4 H's and then there was only 2 in the water, but 2 water molecules has 4 H's. And so you just have to kind of plug a couple of different numbers into the beginning of your reactant of your equation and see what balances out, what doesn't balance, which atoms you need to balance, which ones you don't, and then at the end you can add them all together to make sure you have the right number on each side. So, so again, the numbers of each type of atom on both sides have to be equal. So here's a couple of rules for writing chemical equations. So you want to start with the skeletal equation. If an element occurs only in one compound on both sides of the equation, then balance that first. If there's more than one such element, balance metals before nonmetals. If an element occurs as a free element on either side of the equation, balance it last. We'll do an example so you can see what that means. And it's always good to have a free element because you can save it for last and actually balance out your equation. If the balanced equation contains coefficient fractions, change these into whole numbers by multiplying the entire equation by the appropriate factor. We can do one of those too so you can see what that is talking about. Like if I needed to write 1/2 of an oxygen molecule for whatever reason, I'd have to multiply everything by 2 to get rid of my 1/2 fraction. Check to make sure check to make certain the equation is balanced by summing the total number of each type of atom on both sides. Okay, so let's try one. Let's try to balance this equation here. So let me give you solid aluminum, sulfuric acid. We'll go aluminum sulfate. And hydrogen gas. So we want to balance these. So first thing that we've got to see is if our rules apply here. So if there are any free elements, we do have a free aluminum, we do have a hydrogen molecule here. For hydrogen molecule, I wouldn't call a free element because there's 2 of them, 2 H's. Do we see anything on the same, that's the same on both sides? Sulfates. So we've got some sulfates here and some sulfates here. says that we should do those first. Okay, so let's do this. Notice that I have 3 sulfates on one side and only 1 sulfate on the other side. So right off the bat, I know I need a 3 here, because that 3 times my sulfates will give me 3 SO4s. I guess I don't need to write all that little equation. And over here, I also have 3 SO4s. Now, having 3 H2s here in front of my 3 SO4s means I'll probably put a 3 over here, because 3 times 2 is 6 H's, and now over here 3 times 2 is 6 H's. Okay, 6 H's. So we've balanced the sulfates, the SO4s, we've balanced the H's. Notice that this molecule here has 2 aluminums in it, and so all we have to do now is put a 2 over here. This is the kind of process. You just go through, you pick, you could have started with the aluminums, and that would have been fine. You would have seen 2, you would have had to put a 2 here. Now that wouldn't have helped everything else. You still would have needed to go after your sulfates in order to know how many H2s you need. But that's just the nature of balancing these. You got to start somewhere. You got to work through it. Okay. Let's see. So altogether, we've got 2 Al plus 3 H2SO4 gives us Al2, SO4 3, and 3 H2s. And then you could check and you would see everything is in fact balanced. All right, let's talk about the terminology for whether or not a compound is dissolved in water. So if a compound is soluble in a particular liquid, that means that it dissolves in that liquid. If it does not dissolve, then it is insoluble. And an aqueous solution is one in which a substance is dissolved in water. And these, just by the way, AQ, these are homogeneous. So very evenly mixed solutions. Now, when ionic compounds dissolve in water, they usually dissociate into their component ions. So, for example, sodium chloride, NaCl. When we have it written as sodium chloride aqueous, this means it's dissolved in water. Only dissolved Na pluses and Cl minuses are present. We don't have any of the NaCl formula units that remain together unless we've saturated our solution. Saturated would mean that it is holding the maximum amount that you can hold, and any additional sodium chloride I add will just pile up on the bottom. If you've ever made really sugary Kool-Aid and your sugar doesn't dissolve, that's the problem, is that the water molecules are full. All right, now a substance that completely dissociates into ions in solution is called a strong electrolyte. So sodium chloride is a strong electrolyte. Because again, the definition here is that there are no NaCl's left over, undissolved. So whenever you stick something into a solution and it completely dissolves, that's a strong electrolyte. There are cases that the molecules don't completely dissolve, and those wouldn't be strong electrolytes. So pure water on its own doesn't conduct electricity. There's no ions in pure water, and that's what actually moves the current. So if you could fill up a bathtub of pure water, stand in it, turn on a blow dryer, throw it in the tub, you wouldn't die. Stand in the tub long enough and you'll die, because all of the salts on your skin will start to dissolve into the pure water, and pretty soon that pure water will have ions in it, and then you'll feel that electricity. But if it's pure water and no ions, then no electric charge. On the other hand, solutions containing strong electrolyte solutions will conduct electricity very well. So sodium chloride dissolves in water. Now let's talk about silver nitrate. So a silver nitrate solution, so AgNO3, does not contain also any AgNO3 units. This again would be a strong electrolyte. This thing breaks apart completely. When compounds containing polyatomic ions such as NO3- dissolve, the polyatomic ions dissolve as intact units. So I wanted to show you the contrast between an NaCl breaking up into its units and an AgNO3. Some students want to make there be N minuses floating around and O minuses and Ag pluses, and while there would be Ag pluses, there are no N and O's floating around. The nitrate ion stays together. Okay. All right, so both of these are strong electrolyte solutions. They dissolve completely, and you can see that they maintain their charges while they're in water. Now let's talk about something that does not dissolve. So we've got silver chloride, so AgCl. If you put AgCl into water, and by the way, this is an ionic compound, right? It does not dissolve. So not all ionic compounds will dissolve. AgCl does not dissolve in water, at least not to any observable extent at room temperature. If you put this in really, really, really hot water, it's possible some will dissolve. So AgCl remains a solid, and we would indicate this. In water, it would still be AgCl parentheses little s. This does not dissolve into independent ions. Okay. So when a compound is soluble in a particular liquid, it dissolves, and if it is insoluble in that liquid, it does not dissolve. And so for ionic compounds, the rules of solubility have been deduced for a lot of different compounds for water, and let's talk about those. So compounds that are mostly soluble, we'll talk about first. You can see here, for example, solubility rules indicate that compounds containing lithium ion are soluble, right? Compounds containing lithium ion are soluble. Compounds such as lithium bromide, lithium hydroxide, lithium carbonate, right? Lithium Br, lithium OH, lithium CO3. These would dissolve in water to form strong electrolyte solutions. Okay. Another compound that we see is soluble is NO3-. Compounds containing NO3- are soluble, so AgNO3 and PbNO3. These guys would be soluble and would dissolve in water to form strong electrolyte solutions. Yeah. So let's do an example. Let me ask you guys a question. So I could say, is potassium acetate, C2H3O2, is potassium acetate soluble, yes or no? And you'd look at this table, you'd look at these rules, you'd say, oh, hey, here's potassium. It says compounds containing potassium are soluble. So then you'd say, yes, it's soluble. You could also look for the anion, C2H3O2, acetate. It's also in this list. If it contains that, it's soluble. Why isn't silver chloride soluble? It's got a Cl ion and an Ag ion, right? It says the compounds here that contain Cl ion are soluble. But wait, there's an exception. That's what the rules are. So we look down and it says, for Cl, Br, or I, if they're paired with any of these three ions, then they're not going to be soluble. It says, does the compound also contain one of these? Now in this case, AgCl contains Ag. So does it contain Ag? Yes. Well, then it's insoluble. But if it didn't have one of these three in it, it would still be insoluble or soluble. So we could have, for example, what's a different metal? How about zinc? We could go zinc. Zinc Cl2, right? Cl minus, present, probably soluble. Does it have Ag, H2, Hg, or Pb? No. So then, soluble. Compounds containing SO4. If SO4 is paired with calcium, strontium, barium, or lead, it looks like it won't be soluble. But anything else that sulfate is paired with will be soluble. That's how we use the mostly soluble rules. Now we also have some mostly insoluble rules. Now these are things that are mostly insoluble. Solubility rules state that with some exceptions, compounds containing CO3, 2- carbonate, are insoluble. So these are mostly insoluble. So where the other list told us things that were mostly soluble, these are mostly insoluble, and the exceptions here will be soluble. So let me say that again. CO3, 2- is mostly insoluble. If, though, it's paired with one of these guys, then it will be soluble. And that's because if you notice, lithium, sodium, potassium, ammonium, these are the same ions that were on the previous list, lithium, sodium, potassium, ammonium, that were always soluble. So it makes sense that no matter what they're paired with, they will still be soluble, even if that is something that is normally not soluble. So there's not that many ions here: hydroxide, sulfide, carbonate, and phosphate. Now, this is also the way that you'll probably see this list, usually given in two panels here, the mostly solubles and the mostly insolubles. You can see those ions there. It is worth memorizing these. It'll make your reactions go by a lot faster. But you do have this table to reference. All right, so how do we use our solubility table to then help us with precipitation reactions? So a precipitation reaction is a reaction in aqueous solution that forms a solid. And so remember I showed you sodium carbonate in laundry detergent actually form a solid with the magnesiums and the calciums, right, from the hard water. But a precipitation reaction also happens in this example here. When potassium iodide is mixed with lead-2 nitrate, we see a brilliant yellow precipitate form. And so, again, what we would do is we would start with these two ions, and we're going to have to see what their possible products are going to be. Now, I'm going to show you how to write these in a second, but let me show you that not mixing every two chemicals gives us a precipitation reaction. Here's another example of mixing some potassium iodide, right? Potassium iodide here with lead-2 nitrate, but potassium iodide again here with sodium chloride. In one case, we get a precipitate. In the other case, that we do not get a precipitate. When we don't get a precipitate, we basically say no reaction, because here's why. Ki is a bunch of ions. Sodium chloride is a bunch of ions, right? This is before anything gets mixed together. Everything's a bunch of ions. If we mix everything together and the things that they form, in this case, KCl and NaI, if these things are always soluble, as we just learned, most compounds containing potassium, chloride, sodium, and iodide are usually soluble, then these are going to be dissolved still. They're not going to be, right? Soluble means they're dissolved. So these are going to be found as K+, Na+, I-, Cl-. What's the difference in this chemical, in this system? It started out with 4 ions floating around, and now at the end there's 4 ions floating around. That's what no reaction means. It means no new compounds formed, no new solubilities or insolubilities formed. Okay. So let's do another example. So the key to understanding or predicting precipitation reactions is to understand that only insoluble compounds form precipitates. So in a precipitation reaction, the two solutions containing soluble compounds will combine and an insoluble compound precipitates. So here is that example again. So this is potassium iodide and lead nitrate. Did we already look at this one? We did. So this is a precipitation reaction. We've got potassium iodide floating around, soluble. We've got lead nitrate floating around, soluble. We know this is soluble from our rules. If we jump all the way back, that's not jumping back. If we jump back to our rules right here, we see that nitrate is soluble with no exceptions. That means even if it's paired with lead. So in this case, it is soluble. So we see that before mixing, both of these are dissociated in their respective solutions. Now, in the instant that we mix them together, they are all present in the same solution, and now they're going to allow to react with each other. So what we want to do is predict what's going to form. So let me help. Our original compounds have a positive and a negative ion, a positive and a negative ion. We are going to switch partners. The positives are going to switch places with each other. So the positive potassium that was with the negative iodine is now going to be with the negative nitrate. So they've just switched. And the lead, which was with the nitrate, is now with the iodine. So these are the potential products that could form. Just like in the previous example over here, when I was telling you that we weren't going to get anything, we can still see what we're going to form. We're going to form KCl and NaI, where we started with Ki and NaCl. Now, it just so happens that both of these new compounds are always soluble, and so we don't have any new product. We do the same thing here. We have to check to see if our new products are going to be soluble or not. Now, just looking at this, I can tell you. Well, plus we already know, right? We already know what this is because we looked at the example already in a previous slide. But potassium is on our soluble list. Nitrate is on our soluble list, with no exceptions, either one. So this will be aqueous, meaning no new solid, no precipitate. Iodine is on our soluble list, but it says that anything paired with iodine is usually soluble with the exception of Ag+, Hg22+, and Pb2+. It says if any of the Cl-, Br-, or I- are paired with one of these guys, that they are the exception to the solubility rule. That is the case here. So that's how we know that lead iodide is soluble. Solid. Insoluble. Solid. Precipitation. We know that from the table. And then we would write it, we would reflect that in the phase. So PbI2 would be a solid. Now, anytime that one of these products is a solid, we have a precipitation reaction. If this had been aqueous also, then this would be a no reaction. All right, so let's do one more. We can do another one. Let's write an equation for a precipitation reaction for Na2CO3. This is sodium carbonate and copper chloride. Now they have to start off aqueous or else we wouldn't have any mixing happening. What are the possible products that we're going to get here? Possibly we're going to switch partners and get Na paired with Cl. Do we want to write Na2Cl2 the way that we see it written here? No. That's not how this formula gets paired up. We know Na is a +1, Cl is a -1, so NaCl. Now balancing-wise, there's 2 sodiums and 2 chlorines, so there's probably going to be 2 of these NaCls. The other product we get is copper and carbonate. Now copper's 2+, carbonate's 2-, so we're just going to say that, copper 2 carbonate. So these are the 2 products we get, NaCl and copper carbonate. Now what we have to do is look at our solubility rules and decide what's going to be soluble and what isn't. Now in this case, if we look at the solubility rules, we see that sodium and chlorine, well, sodium's always soluble, no exceptions. Chlorine is soluble unless it's paired with lead, mercury, or silver, and that's not the case here. It's with sodium. So this is aqueous. We're looking at the solubility table to decide this. And then we look at copper carbonate. Now carbonate is on the insoluble list. This is an insoluble compound, normally. And we would look to see if copper is one of the exceptions. Now when you look at that list, you see that copper is not one of the exceptions. So this does not change its insolubility. This is insoluble. All right, so now we have our formula, or now we have our 2 phases, and we can actually say if this is a precipitation reaction or not. In this case, it is. And so we want to write it out now as a precipitation reaction. So we would say Na2CO3 aqueous plus CuCl2 aqueous gives us 2 NaCl aqueous and a copper 2 carbonate solid. That right there from the aqueuses is the evidence of a precipitation reaction. All right. Balancing is a separate thing, right? We could have done this and then balanced it afterward because we would have had to account for the multiple sodiums and chlorine ions. Now, what we do after we've got a, let's say, gas evolution or precipitation or even an acid-base reaction is we write chemical equations for the reactions for both the molecular and complete ionic equations, and then we write something called a net ionic equation. So let's talk about those. So the molecular equation is the equation showing the complete neutral formulas. You can see that here. The complete ionic equation is showing all of the ions. So anywhere that you see aqueous, 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 we want to take those ions and show them in their ionic form. So we call it the total ion equation. The only ones that aren't ions are things that are solid. We do not separate solid, liquids, or gaseous compounds. So just the ionic stuff. And that kind of looks like this. So for this example, you can see silver, nitrate, sodium, chlorine, silver chloride didn't get separated, another sodium, another nitrate. We look at what are called spectator ions. Spectator ions are going to be in their ionic form on both the reactant and product side of the equations. We can essentially cut these out when we write what we call the net ionic equation. Because NO3 minus is NO3 minus on both sides, we don't need to talk about it when we show the main point of this reaction, which is that silver will react with chlorine and make silver chloride, right? The sodium and the nitrates are just floating around in both cases. We don't have to talk about them. So then we would summarize our equation as, we could write it right here, Ag plus Cl minus gives AgCl. And then with some phases to indicate that they are an aqueous solution. And if we have to balance it, we would balance it as well. So, molecular equation is the chemical equation showing the complete neutral formula. The ionic equation, total ionic or complete ionic, shows all of the species as they actually are. And the net ionic only shows the ones participating in the reaction. Okay? All right, so we've talked about combustion, we've talked about precipitation. Let's talk about acid-base, gas evolution, and redox. So acid-base reactions are those that involve forming a water upon mixing of an acid and a base. So acid and base reactions are also called neutralization reactions, and generally form water in what we call an ionic compound or a salt, and that usually remains dissolved in the solution. So the net ionic equation of most acid-base reactions would be as follows. H plus Cl minus plus Na plus OH minus gives us H2O plus Na plus Cl minus Na plus Cl minus spectators. H plus OH minus is H2O. This is the net ionic equation for almost every single acid-base reaction. They all have hydrogens, they all have hydroxides, and they all make water. And a salt, water and a salt, which is just a dissolved ionic compound. You can imagine if this wasn't dissolved, if it was a non-dissolved ionic compound, then would this still be an acid-base reaction, or would it also be a precipitation reaction? It would be a mix of the two. I don't know that there are any acid bases that would give us this, but conceivably, if this is what we ended up with, this would be a precipitation reaction / an acid-base reaction, though, again, acid-base reactions are going to depend on these guys as much as having a soluble salt that forms. Let me show you some common acids and bases. So here's some common acids on the left, common bases on the right. You'll notice that our acids have H's in front. This is going to be the source of that H that makes the H2 part of the water, or the H and the OH part of the water. And then here's the rest of the water molecule, the OHs. While some of our acids actually have multiple hydrogens that they can donate, this one H2SO4, some have multiple OHs as well. So let me show you another example of an acid-base reaction. So let's take something like barium hydroxide. So this is the base first, and let me add an acid, maybe HNO3. So double displacement is what we're going to call this, and I'll go over that in a second, but essentially we're going to switch cations, right? Switch partners. So it helps to know the charges on all of these guys. So Ba is 2+, so when it forms up with nitrate, we're going to need a couple nitrates. And then when the H pairs up with the OH, there's 2 OHs here, so we're actually going to end up with 2 waters, or 2 HOHs. And you can see here that is going to give us the acid, right, base neutralization reaction. We also get a salt. If you remember, nitrate is on the always soluble list, so even paired with barium, this would be aqueous. Oh, water is a liquid, not dissolved in a liquid, so we wouldn't call it aqueous. We would just call it a liquid. So our net ionic would be H plus, OH minus. Technically in this one it would be 2 and 2 make 2H2O liquids. Again, acid-base reaction. Acid has an H, base has an OH. That won't always be the case, and when we get to the chapter 14 and look at acids and bases, you'll see that that's not always the case. Okay, gas evolution reactions. So we've looked at combustion, precipitation, acid-base, which always gives a salt and water, and now combustion. Gas evolution. So gas evolution reactions give off gases. There's only a few types of reactions that will actually do this, and only a few gases that are evolved. So you can see here, if we're dealing with sulfides, we might get some hydrogen gas, hydrogen sulfide gas. If we're dealing with carbonates and bicarbonates, meaning they contain CO3 minus, then we get CO2 as the gas. Sulfides, by the way, are compounds that contain S2 minus. Sulfites and bisulfites come in the SO3 category. These give us SO2 as a gas. And then ammonium, specifically having NH4s in our compounds, this yields ammonia gas, NH3. So let me kind of show you a more detailed reaction. So here you can see examples. So typically we would be adding some kind of acid or some kind of compound that is going to double displace. Double displace means switch cations, switch partners, with whatever is in our second thing here. These, of course, containing the reactant type, sulfides or carbonates or sulfites. And then you can see that some of these have intermediary products or intermediate products. So, for example, H2CO3, before it just breaks down into CO2, actually, well, it breaks down into CO2, but the way that the CO2 comes out of that molecule, you can see it here. These break down to release a water molecule as well. So all of the ones that have intermediates, which are these three, they all also produce a water molecule. That's how the gas can look like it does, right? If you take H2CO3 and remove an H2O, you're only left with a CO2. That's where the gas comes from. And so that's just the only time you don't have to do that is when we're dealing with sulfides, because they produce their gas directly. Now, I typically only will ask you guys about carbonate compounds. The lab we do will have a carbonate compound in it. So at least be aware that if you are mixing chemicals together and your hydrogens are going to pair up with carbonates, that you're most likely going to end up with this hydrogen carbonate or carbonic acid molecule that breaks down into a water and a CO2. And so gas evolutions, of course, are easy to spot because they're all aqueous until there's a gas formed. We can do an example of that. Let's do an example. So let me give you something like, I don't know. This is nitric acid. Let's react that with sodium carbonate. Double displacement. I'm going to switch the partners. So the H will switch off to go where the N's are, the NA's, sorry, and the NA will go where the H is. I'm going to need 2 of these. So we'll see. We're going to get H2CO3, and we're going to get NaNO3. Now I know I needed 2 because I have 2 NAs here. So that means I'm going to need 2 of these nitrates. So I need a 2 there. That also gives me 2 H's, so I can put my 2 H's there, where the sodiums were. So these are the 2 compounds I get. Now, H2CO3 is one of those that you want to recognize as not being done reacting. It breaks down into water and CO2 gas. So all 3 of these things would be the products at the end, and then you could check to see if that was balanced or not. Now, your stomach acid in your stomach can be neutralized by antacids that you get over the counter and work essentially as bases. These things contain magnesium carbonate or aluminum hydroxide, compounds that are going to react with the stomach acid, which is usually HCl, in order to produce water. And in lots of cases, or in some cases, um, um, what's the word? Carbon dioxide. They produce gas, and so this is usually the bubbles you see in like an Alka-Seltzer, but it's also going to result in some burping. Okay, let's talk about redox reactions. Now, reactions that involve the transfer of electrons are called oxidation reactions, or redox for short. Redox reactions are responsible for rusting of iron, the bleaching of hair, production of batteries, and the electricity flow in batteries. And many redox reactions actually involve oxygen, directly involve the oxygen molecule. So fundamental definition of oxidation is loss of electrons. Fundamental definition of reduction is gain of electrons. And so this can help you out. Oxidation is loss, reduction is gain, oil rig, or Leoger, lose electrons, oxidation, gain electrons, reduction. So that should help. We also think of oxidation as the increase of oxygens or the decrease of hydrogens. When you add oxygens or remove hydrogens from a molecule, we call that oxidation. Opposite is true for reduction. It's the decrease of oxygens and the addition of hydrogens, in addition to these definitions involving electrons. Oxidation and reduction must occur together. If one substance loses an electron, oxidation, another substance has to gain that electron, reduction. They don't just float off into space. And so these need to be coupled. And for now, you just need to be able to recognize simple redox reactions, okay? Again, a reaction can be classified as redox, if it meets any of the requirements, reacts with elemental oxygen. So redox in general. Reacts with elemental oxygen, a metal with a nonmetal. These are going to be redox reactions, or just electron transfers. E-transfers. All right, and then like we mentioned, combustion reactions are actually a type of redox reaction. Combustion reactions are characterized by something reacting with oxygen. So let me give you a couple. So start off with a metal or like a oxidation, either rusting or combustion. So we know the combustion one, CH4. Actually, let's do a fun one. Let's go C4. No, what do I want? Yeah, we'll do C4H10 plus O2 makes CO2 and water. So right off the bat, this has an O2 molecule in it. We know this is combustion. Now let's balance this one for fun. So we see that there are 4 carbons. So I'm going to put a 4 here. Makes my carbons the same. I also see that I have 10 H's over there in that molecule. 10 H's. And over here I only have 2. So I'm going to put a 5 here. All right. So let's count up the oxygens. So that's because 4 carbons and 4 carbons, 10 hydrogens and 10 hydrogens, but this is 4 times 2, 8 plus 5 is 13 oxygens. And over here, I have 2. So I need to add a number there that's going to make my number 13. And that's not easy, right? So let's say, what is 13 oxygens? Is that 24 oxygens? Let's see. Sorry, so 1 oxygen molecule comes with 2 oxygens. So 12 oxygen molecules is 24 oxygens, right? That's too many. 6 oxygen molecules is 12. 7 oxygen molecules is 14. So that's too many. I need 6.5. I need 6.5 oxygen molecules. All right, how do we write 6.5? Well, let's write it as a fraction. Is it 13 divided by 2? Is that 6.5? 13 over 2, because 12 over 2 would be 6, and 14 over 2 would be 7. So yeah, this is 13 over 2 is 6.5. Okay, so you're like, why am I doing this? Watch this. All right, 13 over 2. Now I have the right number of oxygen molecules, because that's 6.5 oxygen molecules. 6.5 times 2 is 13. We have the right number of oxygens. But we don't want to have fractions in our formula. Remember, this was when we were balancing. I said that if you have fractions, you got to get rid of them. So what we're going to do here is double everything. We're going to go times 2, times 2, times 2, times 2. That gives us 2 C4H10s plus 13 O2s plus 8 CO2s plus 10 H2Os. Do a quick count. 2 times 4 is 8 carbons, 8 carbons. 2 times 10 is 20 hydrogens. 10 times 2 is 20. 13 times 2 is 26 oxygens. 8 times 2 is 16 oxygens, plus 10 more oxygens is 26 oxygens. So that is how you take care of those funny, difficult to balance equations. Did I get sidetracked? We did. O2, redox. Here's another one. Ti plus O2 is TiO2. Or iron plus O2 is FeO2. These are elemental oxygen. This is redox. This is what we would call rusting. This is oxidation. All right, so if you don't see the O2, here's another way to tell. So what do we have here? We have metals reacting with nonmetals. Chlorine and sulfur are on the nonmetal side of the periodic table. So sodium and potassium are on the metal side. Metals and nonmetals are redox. The reason metals and nonmetals are redox is because of the electron transfer. We know that over here, these guys have charges on them. Well, how did they get charges? Sodium had to lose an electron, right? Chlorine had to gain an electron. So metals and nonmetals are one way of recognizing it. Sometimes you actually do see the charge change, though. Let me show you. Let's say that I have zinc 2 plus reacting with copper. And that yields copper 2 plus and zinc. You can easily see here that there's electron transfer. You can tell that zinc gained some electrons because it went from being negative a couple of electrons, missing 2 electrons, to now having all the electrons it needs. This guy went from having all the electrons it needed to now missing 2 electrons. So somebody gained, somebody lost. So recognizing molecular oxygen, recognizing metals and nonmetals, recognizing electron transfer. That's redox reaction. We're going to go way deeper into it later in chapter 16, but for now, you just need to spot it. Okay, so as far as chemical reactions go, they can be summed up as precipitation reactions, forming a solid, acid-base reactions, water and a salt, that's aqueous. Gas evolution reactions, forming a gas. Oxidation reactions, we saw reacting with molecular oxygen, electron transfer, or metals and nonmetals. And as a subsection of that, combustion reactions do count as oxidation reactions. So 5 types, specific types, but really 4 categories. Now, back to the other types of reactions, we do have what we call the general types. And so these are synthesis or combination, decomposition, single displacement, and double displacement. So let's look at some examples. As far as combination goes, so here is when we take 2 elements or 2 molecules and 2 substances, A and B. Those can be atoms, they can be molecules, they can be people. Mush them together, they become one thing. So I guess they can't be people. A and B now become AB, whatever that is. And so if they're elements like sodiums and chlorines, well, they could become sodium chloride. That is synthesis. So 2 reactants, 1 product. Decomposition. This is when we have one reactant and get two products out of it. So something breaks apart. This could be a molecule dissociating into two others. This could be atoms unbinding from each other and leaving as their own gases, their own pure elements. So water becoming hydrogen gas and oxygen gas is actually a good example of what we call hydrolysis. Hydrolysis, cutting. No, that's not hydrolysis. Electrolysis, sorry. Hydrolysis is something different, where we add a water molecule to cut a bond. Here, we're actually splitting water. That's called electrolysis, using electricity to break bonds. Okay. We have synthesis reactions, can be displacement or single displacement. So single displacement is when we have one ion and then a paired compound, and that one ion comes in here and switches places with one of the two. So in this example, we have solid zinc, and then we have copper chloride. And what happens is the copper is going to switch places with the zinc and form a plate, copper solid, and the zinc will dissolve and pair up with the chlorine. So we are switching partners, but only one thing is switching, where in double displacement, we get, two new compounds. So here A is taking B's place. A could also take C's place, to be fair. It could be AB, and we could displace C. If we're talking about charges and we want to say that A is positively charged, then it can only displace B, which is usually the case for us. Our A's and C's will be positives, our B's and D's will be negatives, and then they'll just rejoin up in that way. Do I not have a double displacement? Well, we've been doing double displacement all afternoon. All of those reactions we looked at today were double displacement reactions, with the exception of the combustion. All right, so in a double displacement reaction, though, we get those two elements or groups of elements exchange places. All right, and those are the ones that usually will give us the precipitation and the acid base and the gas evolution. All right, so all of those can be summarized here in this little table. And so as far as review, we went over chemical reactions, how one substance or element can change into another. We looked at the evidence, and really only absolute evidence from a chemical analysis will show us, but often we can look at color change, formation of a solid or precipitate, formation of a gas, emission of light, or the absorption or emission of heat to tell. Chemical equations must be balanced to conserve matter, or to reflect the conservation of matter. Aqueous solutions and solubility, we went over that. If a substance dissolves, it's soluble. If not, it's insoluble. And we looked at how we can use the table of solubility to predict if a compound will be soluble or not. We'll talk more about solubility in the solutions chapter, in chapter 13. We looked at some specific types of reactions: precipitation, acid-base, gas evolution, redox, and combustion, and then some general classifications. And then hopefully these learning objectives will help you guys in your studying. All right, guys. Don't forget to be using the discussion board. Put down stuff that you have problems with or things you'd like to see more examples on, and I will work on getting those for you guys. All right, guys. See you in the next video.